Okay, so in this video we are going to look into calculation of angular momentum for a rigid flat plate with rotations in three-dimensional space. The reason we picked this problem is because rigid body angular momentum of rigid bodies pose some confusions because of the fact that there is a distribution of mass, and also because of the fact that three-dimensional motions of rigid bodies can contribute some complexities in the calculations of angular momentum. So we are going to solve this problem using two different methods. The goal is to find the angular momentum of this square flat plate. We'll solve using two different methods between the multiple videos that we'll make on this, and then ultimately we'll calculate the rate of change of angular momentum for this rigid body. So just to give you an overview of this system, here is a square flat plate of length, the sides are of length L, and this corner A is fixed, and what is happening is that this flat plate is being rotated by an angular velocity capital omega about the inertial z-axis. So this capital Z is the inertial fixed z-axis, and while that rotation is happening, the square flat plate is also oscillating by an angle theta and angular velocity theta dot, which are of course variable, and that angle is being formed by this diagonal of this square flat plate with the inertial z-axis. Our goal is to find the angular momentum of this flat plate about the point A. So the point A is a fixed point. So let us write down the salient features or the salient points of this problem. So firstly, determine angular momentum of square flat plate about A. So we want to find out the angular momentum about the point A. Of course, we need to mention that the plate is of mass m. The angular velocity capital omega is constant. The mass and length are all given, so that's the this is the setup of this problem. So the first approach that we are going to take, okay, so before we start working on the problem, we also note that this angle theta represents the tilt of the diagonal of this square plate from the inertial vertical, that is represented by the angle theta. Note that because this is a square, this x-axis and this y-axis, they are body fixed, okay, and this x and this y are fixed to these two edges of the square plate. Z is mutually perpendicular to the two. This is small z, or this is a rotating z coordinate, and this is mutually perpendicular to x and y. We also indicate the centroidal or the center of mass axis. X sub c and y sub c are body fixed, that is, they are fixed to the square plate, and they are passing through the center of mass. x sub c is parallel to these two sides and y sub c is parallel to these two sides. Z sub c has the same direction as z, with the exception that it passes through the center of mass O. Okay, so just point out that O is the center of mass or center of symmetry. All right. So in this case, you can calculate the angular momentum using two ways. One is to say that the plate has an angular momentum about its center of mass, and the center of mass, by virtue of its velocity about the point A, has got an angular momentum about A itself. That is the approach that we are going to show in this video. The other approach that you can take is because this point A is a fixed point, and the rigid body is purely rotating about the point A, therefore you could directly find out the angular momentum about the point A. I will take that as a second approach, and in this first approach I'm going to take the I'm going to first find the angular momentum about the center of mass and then find the angular momentum of the center of mass about A. So I'll take that first approach because that is a little bit more intuitive, and if you consider different types of rigid body motions, then that is probably a more conventional way of solving these, because it helps us visualize this problem, and it also helps, by the way, in formulating the moment of inertia tensor. So whenever you consider your reference point as the center of mass, and especially when it is aligned, when the coordinate system is aligned with the axis of symmetry, then you have the benefits of having a simple moment of inertia tensor. So we will take the approach that angular momentum about A is equal to, of this square flat plate, is equal to the angular momentum about the center O plus let's see, AO cross m times VO. Okay, so this part is the angular momentum of the rigid body about its center of mass, and this is the angular momentum of the rigid body due to the motion of the center of mass. So we start this with the calculation of H of O. This part is quite simple because our and we must note that we are going to express everything in the XC, YC, ZC triad will be used. And if you think about it, if you use the XC, YC, ZC triad, the answer that we will get would be the same answer that we would get if we chose X, Y, Z as the triad. And the reason is X is parallel to XC, Y is parallel to YC, and Z is parallel to ZC. Okay, so that's why we'll get the same answer. We note that XC, YC, ZC are body fixed and through the CM, the center of mass, and along axis of symmetry. So this actually simplifies some of the calculations that are involved in H of O. So in this case, because the triad has these properties. The moment of inertia tensor only has the Ixx, Iyy and Izz components. All the product of inertia terms are equal to 0. So essentially what we have is we have Ixc omega c omega xc Ic plus Iyc omega yc jc plus Izc omega zc kc. So here we note that Ic, jc and kc are unit vectors along xc, yc and zc respectively. Okay, and the angular velocities omega xc, omega yc, omega zc, as the variable names suggest, they are along these along this triad, along the axis of this triad. And similarly, Ixc, Iyc and Izc are the moments of inertia along the axis of this triad. So we can very quickly come up with the expressions for Ixc. Because this plate does not have any thickness, so the moment of inertia of this plate about the xc axis is going to be nothing but 1/12 ml squared. Similarly, Iyc is also going to be 1/12 ml squared, and Izc is going to be the moment of inertia about the axis that is going through the center and going out of the surface. So it is going to be the moment of inertia in the x plus the moment of inertia in the y direction, and that comes from the basic equations of moment of inertias for any flat surface. Okay, if z is pointing perpendicular to that flat surface and x and y are along the flat surface, then the moment of inertia along z, which is perpendicular to the flat surface, is equal to the sum of moments of inertia about the x and y axis, which are along the flat surface, and that comes from the definition of the moment of inertia. So in this case, it's going to be 1/12 ml squared plus 1/12 ml squared is equal to 1/6 ml squared. You can of course look up the formulas for these moments of inertia in any textbook and you will be able to find them. So we have the moments of inertia sorted out. Next we go to the angular velocity, and our goal is to find the angular velocity of this disk, and we are going to express it using this triad xc, yc, zc. So first we note that the angular velocity, this omega angular velocity, is in the inertial k direction. So we have a omega in the inertial k direction. Okay, this is not the direction of interest, so we are going to resolve this angular velocity. Secondly, we have an angular velocity due to the angle theta, and we can see that that angular velocity will always be in the direction of zc. So it is going to be theta dot times the unit vector in zc, which is kc. So now and this is because you can imagine that as the disk rotates and turns, the disk rotates by the angle theta and it turns about the vertical axis. At any given arbitrary orientation, always ZC is going to be perpendicular to the surface, the flat surface. And because the angle theta is always on that flat surface, so therefore theta dot is always in the direction of ZC. Now let us get back to this angular velocity, that is the constant angular velocity about the inertial axis Z. Now this angular velocity needs to be resolved along this triad, which is of interest. So we can see that capital omega has this direction, and you can see that this direction makes an angle of 45 degrees minus theta with the xc axis, and that is simply because this direction is the or this line rather is the diagonal of the square, and so the diagonal of the square will make a 45 degree angle with the x-axis and with the y-axis. And so the angular velocity is in this direction, and it makes a 45 minus theta angle with the x-axis. So you have a minus omega cosine of 45 degrees minus theta in the IC direction, and minus omega sine of 45 degrees minus theta JC, and that is because you see the angular velocity vector is going to be somewhat like this, and it's going to have a component in this direction. So angular velocity vector is going to be pointed this way, so it's going to have a component in this direction, which is in the negative xc direction, and it is going to have a component in this direction, which is in the negative yc direction. And then we are going to have the theta dot kc. So this is our angular velocity. Now so we can now plug these values into this equation for HO and find out the angular velocity about the center of mass. But before we do that, because it's just plugging in numbers, we will determine these components that are needed to find the angular momentum of the center of mass with respect to A. So first let us formulate the vector AO, which is the vector going from A towards O. So AO is the vector that goes like this, right? And so AO is given by, we note that this distance is half the diagonal, and the diagonal is square root of L, because the the diagonal is square root 2 times L, so the half of the diagonal is square root 2 times L divided by 2, so that is L over square root 2. So the length of AO is L over square root 2, and it makes cosine 45 degrees with the x-axis, xc axis, and sine of 45 degrees with the yc axis. So since sine of 45 and cosine of 45 are 1 over square root 2, then you have L over 2 IC plus L over 2 JC. All right. Now next we want to find out the velocity the velocity Vo. So O is undergoing pure rotation about the point A, and so therefore Vo is equal to omega cross AO and so that needs to be so essentially this is omega C cross L over 2 IC plus L over 2 JC. All right. So next what we do is we carry out these cross products. So we note that we have the following triad. We have IC, JC and KC, which is a right-handed triad, and so this is the convention for doing the cross products. We have the expression for omega C, so therefore omega C cross IC, which is the first term here, is going to be this expression cross IC. So we have IC cross IC is 0, JC cross IC is negative KC, so we will have omega sine of 45 degrees minus theta KC, and then we will have KC cross IC, which is JC, so plus theta dot JC. Alright, and similarly we will have omega C cross JC, and that is going to be which is basically the second term, so that is going to be I cross J, so I cross J is going to give us K, so we will have minus omega cosine 45 degrees minus theta KC, and J cross J is 0 and K cross J is minus I, so we'll have minus theta dot IC. Alright, so therefore we have the following expression for VO. So the velocity of O is then L by 2 times omega sine 45 degrees minus theta KC plus theta dot JC plus L by 2 times negative omega cosine 45 degrees minus theta KC minus theta dot IC. Or in other words, this becomes minus L theta dot over 2 IC plus L theta dot over 2 JC plus L capital omega over 2 times sine 45 degrees minus theta minus cosine of 45 degrees minus theta KC. Let me just check if I have the right expression. Yes, the right expression. So that's the expression for VO. Now if we go back to our formulation of the angular momentum, we see that we need AO cross MV V naught, So let us check out our expression for AO. So we need to do AO cross MV0, and AO is quite a simple expression. It's L over 2, so it's L over 2 IC plus JC cross VO, right? So we have so first let us carry out this cross product between IC and this expression. So IC cross IC is 0, then we have IC cross JC is KC, so L square theta dot divided by 4 KC and then IC cross KC is minus JC, so it's going to be minus L squared capital omega over 4 times sine 45 degrees minus theta cos 45 degrees minus theta. We are doing I cross K, so that is going to give us J, and I cross K gives us negative J, so that's why we have this negative term here. We should have an M here as well, right? So let's put the M here. Okay, and then continuing, this is just 2 expressions, and there are 2 more expressions to be derived, and the first one is JC cross IC. JC cross IC is going to give us negative KC, so we are going to have and the negative is going to multiply with this negative to give us a positive, so we will have plus ML squared over 4 theta dot KC. Okay, and then JC cross JC is 0, JC cross KC is going to give us IC, so we will have so that's a positive, so then you will have ML squared capital omega over 4 times this expression, so that's sine 45 degrees minus theta minus cosine 45 degrees minus theta, and this is going to be IC because it's J cross K. Alright, so I'm sorry, I had gone a little bit too lower down the page for the screen, but at this point we have the expression for AO cross MVO. So therefore the net angular momentum H of A is equal to HO plus AO cross MVO. So we put together the expression for HO, and that is IX omega X IC, so that is 1/12 ml squared was the moment of inertia in X direction, times the angular velocity in X. The angular velocity in X is negative omega cosine 45 degrees minus theta. That's in the IC direction. Then we have plus 1/12 ml squared times the angular velocity in the J direction, which is also negative omega sine of 45 degrees minus theta. That's the component of the angular momentum of the plate about the center point O, plus you have the moment of inertia about z, which is 1/6 ml squared times the angular velocity in z, which is theta dot kc. So this part is our h of O, and then we add the AO cross MVO, of course, which we have found over here. So now we are ready to write the overall expression. So if we consider this expression here, so let me just see if I can indicate. So this expression and this expression need to be added together. So let's do that. So we have first we'll identify the terms in the I direction, so that's this term, and here we have this term in the I direction. So we will have ml squared capital omega times 1/4 sine of 45 degrees minus theta minus 1/4 cosine of 45 degrees minus theta minus 1/12 cosine of 45 degrees minus theta, and this is in the IC direction. The next term is going to be the term in the J direction, JC direction. So again we take this JC component, we take this JC component, and we add them together. So we will have, I think looks like it's going to be a negative term overall. Yeah, so let's just write it as ml squared capital omega times, so that's the JC, ml squared capital omega times negative 1/4 sine of 45 degrees minus theta negative, or rather plus 1/4 of cosine of 45 degrees minus theta, and here we will have minus 1/12 sine of 45 degrees minus theta. So the expression is getting long, but that's okay. We have ml squared theta dot over 4, ml squared theta dot over 4, and you have ml squared theta dot over 6th. So you essentially have 1/4 plus 1/4 plus 1/6. So that is half plus 1/6, and half plus 1/6 is 2/3. So we will have plus 2/3 ml squared theta dot kc. Alright, there is just a little bit of simplification that is left. And we'll have our expression for the net angular velocity about the point A. So h of A then is equal to, consider these terms here, you have two cosine 45 minus theta terms. One has 1/4 and another is 1/12. So 1/4 plus 1/12 is 4/12, which is 1/3. So it's going to be ml squared capital omega 1/4 sine of 45 degrees minus theta minus 1/3. Let me think. Yeah, 1/3 cosine of 45 degrees minus theta. I see. Here we have again a 1/4 and 1/12. They get added to give us 1/3. So minus 1/3. So we will have plus ml squared capital omega times 1/4 cosine of 45 degrees minus theta minus 1/3 of sine 45 degrees minus theta. That's in the JC direction, and then we'll have 2/3 of ml squared theta dot kc. Okay, so let me now check if this is okay or not. Think it is okay. It should be. We have in the IC direction we have 1/4 sine minus 1/3 cosine. The JC direction we have 1/4 cosine minus 1/3 sine, and here you have the 2/3 ml squared. Yeah. So this is good. You can also express this in terms of, see, all these 45 minus theta is cosine of 45 minus theta is actually equal to cosine of 45 plus theta, and similarly cosine of 45 minus theta is equal to sine of 45 degrees plus theta. So you can express it that way, also depending on how you want to express it. But this is good. This is the calculation of the angular momentum of this disk, not this disk but this square flat plate, in terms of the point A. So just going back to where we started, we set out to calculate the angular momentum of this square flat plate as it turns about this vertical direction with a constant angular velocity, but also swings about the point A in the lateral direction. And we found the angular momentum about the point A in this using this approach, where we first found the angular momentum about the center of mass and then found the angular momentum of the center of mass due to its velocity about the point A, and we added it up. So that's it for this video. In the next video we are going to show the same angular momentum calculation but directly about the rotation center, which is point A. So thank you so much. This is part 1 of this angular momentum calculation series. Thank you.